in the study. And a specific slope estimate depends on the particular range of the X and Y scores, the type of participants in the sample, and within the context of the specific set of predictor variables. And it's this last one that I really wanted to talk about. Let's give an example of this. Let's look at the alcohol metabolism data set that's in Chapter 11 case studies. When men and women of the same size and drinking history consume alcohol in equal amounts, the women on average carry a higher concentration of alcohol in their bloodstreams. Enzymes that metabolize alcohol are supposedly more active in men than in women. A team of Italian researchers studied the extent to which the activity of the enzyme explained the first-pass alcohol metabolism in 18 women and 14 men. All of them were volunteers living in Trieste. 3 of the women and 5 of the men were also alcoholic. All of the subjects received ethanol at a dose of 0.3 grams per kilogram body weight. And the idea was to measure their metabolism. One of the things we wanted to look at is, can the differences in the men and women be explained by postulating that men have more enzyme activity in their stomachs? And related to that, are the answers to this question complicated by the alcoholism effect? So a tentative model for this particular data set is going to contain the parameters whose values, or contain the variables whose values answer the questions in a straightforward manner. So we might not want to start out with all of the variables in the model. We might just want to start out with a few that we think might be the best ones. We should include potentially confounding variables as well, and include features that capture the important relationships found in any initial graphical analysis that we see. Like, for example, if we're looking at scatter plot matrices, we'd want to be sure to include all the variables that seem to be highly correlated with the response. Now, one way we can look at this is the inferences on partial slopes. So we've already seen this, and the inferences on partial slopes is just kind of a fancy way of saying, looking at the individual test for each slope in the model. And this will give us an idea of whether or not that particular slope is statistically significant for the model. If it isn't, we can exclude it. Now, one of the sides of this that I want to show you is that actually the test statistic, or the standard error for the slope in the model, actually has this component in it, which is called the variance inflation factor. We can divide an estimate for the slope by its estimate of standard error, and I've rewritten the estimate of standard error in this formula in an algebraically equivalent way, but in this way it shows you precisely, or exactly, that 1 minus r squared is actually included in the model, but this is a special r squared. It's the r squared for that value of x as the response variable with all the other values included in the model. So what this r squared is it tells us the proportion of variance in the particular explanatory variable that's under investigation with this slope, including all other explanatory variables as the predictor. What does this mean? That means that if this r squared is large, then we would have that this particular variable, the value of this particular variable, is well predicted by the other variables in the model, and we don't need it. If this r squared is small, then the other variables in the model don't do a very good job of predicting the variable, and we do need it in the model. So this is what we call the variance inflation factor. And we'll come to this when we look at collinearity, which is the idea that some explanatory variables can be well explained by other explanatory variables in the model, so we don't need to include all of those because it would be redundant. So let's look at this first pass model. In this first pass model, we have here the SAS output looking at the intercept. In the model, we have a term for gastric, which is the gastric enzyme activity. We also have indicator variables for female and alcoholism. We also have interaction variables for gastric times female and gastric by alcoholism. Those are called GAST-FEM and GAST-ALCO, and down there at the bottom of the model. And then we have the three-way interaction, which I've termed three-way in the model, for a three-way interaction between gastric enzyme activity, the gender, and whether or not the individual is alcoholic. If we look at the significance test for these, we see that the alcoholism variable, the interaction between the gastric enzyme activity and alcoholism, and the three-way interaction are all not statistically significant. So these are values that we might want to exclude from the model. But how do we know for sure? Well, I guess in statistics you can never know for sure, but you can take a really good guess. One of the things we want to look at is whether or not any of these variables might be collinear with other variables that are already in the model. And how do we do that is by looking at the variance inflation factor. So for the metabolism data, we see that the alcoholism indicator variable has a variance inflation of 11.9. And the interaction between gastric enzyme activity and alcoholism has a variance inflation factor of 9.05. Now, what do these values mean? Well, there's really no nice interpretation of the variance inflation factor. We're just looking for relative differences. And the current wisdom says that if a variance inflation factor is greater than 10, then you should worry about that variable being redundant for the rest of the model. Here we have alcoholism that is at 11 and another one that's at 9. So it might be a good idea to exclude these two again, but we're not sure unless we look at something different, and that's called a partial residual plot. The idea behind a partial residual plot is to estimate the function of one of the explanatory variables with a linear regression, and then obtain the estimated coefficients of the linear regression of that response on x1 and x2. So we have two explanatory variables. We're going to use those two to estimate the response. Then we will compute partial residuals, and the partial residuals are given by the observed response minus the linear regression equation, including x1 and x2 in the model. Then we're going to plot the partial residuals. I'm sorry, I misspoke. The partial residuals are the response, or the observed response, y, minus the term b0 minus b1 x1. So this is just the linear regression with x1 in the model, and then we plot these partial residuals versus x2. What we're looking for is if that plot looks linear, then the variable x2 should be included in the model with the linear term. So let's look at partial residual plots for the alcoholism data. Remember I said that the variance inflation factor for the alcoholism indicator variable seemed to be a little bit large. And if I look at that variable, this is in the bottom left, the partial residual plot for this, I see that there is some evidence of a linear relationship after we've adjusted for the other variables in the model, but it's not that strong. So it might be that alcoholism, that particular indicator, should be removed from the model. If we look at the other ones, for example, gastric, that is an example of a variable which likely should stay in the model because that relationship is very strongly linear even with the other variables accounted for. So the partial residual plots, in addition to regular residual plots and looking at variance inflation factors, can help us determine which variables should stay in the model and which variables we should drop out of the model, at least temporarily, until we can figure out whether or not until we can figure out what the best model is for the particular response of interest. I've said this several times already, but least squares is not resistant to outliers. But there are a few strategies for dealing with outliers, and this is what I want to outline. One of the ways we can deal with outliers is to use a robust regression procedure. And that is useful when past experience indicates that the response distribution tends to have long tails. In other words, it's prone to outliers. Therefore, any kind of remedies we might do on the data set and trying to run least squares would still give us outliers and give us parameter estimates that were not valid. If that's not the case, or if we don't want to use a robust regression procedure, we can use least squares, but we have to examine the outliers and influence closely to see whether suspect observations are indeed influential, why they are influential, and whether or not they provide some interesting information about the process under study. So what do we do? If the observation differs from the remaining data in its explanatory variable values, if it's in a sparsely represented region, meaning that there aren't that many values of y that are measured for those range of values of x. Let's say, for example, you have values of x that range from 0 to 15, and for some reason you have a large number of observations in there, and then for some reason there's a few measurements where x is ranging from about 20 to 25, but there are only 3 or 4 of those. We might want to just restrict the range of the analysis in that case, because those small amount of points that are out there in a different range are going to affect the linear regression. So by restricting the range, We get rid of the influence of those points. But again, when we write up the results, we have to tell the individuals that we're writing to that we restricted the range of the study and why we restricted the range of the X variables. If the observation is not unusual in its explanatory variables and no other explanation can be found for its being unusual, we can't omit it. So our last resort then is to report results both with and without the observation. So here's kind of an outlier decision tree that I've outlined. The first question to ask yourself is, do the conclusions change when the case is deleted? If yes, then there's a reason to believe that the case is there a reason to believe that the case belongs to a different population other than the one under investigation? If you believe that the case belongs to a different population, then omit the case and proceed. If not, if you can't justify the case belonging to a different population, meaning that it's so different that we would expect that the population under study would never produce a case that large or that small, then we need to ask ourselves, does the case have usually distant explanatory variables? If the case has unusually distant explanatory variables from the rest of explanatories in the model, so this would be the restricted range case I talked about earlier, we would omit the case and proceed and report conclusions for the reduced range of explanatory variables, again explaining why we reduced the range. If no, we can't say too much more from that. More data or clarification is needed to resolve the question. Now, if there's no reason to believe that the case belongs to a particular or different population than the one under investigation, we're going to have to proceed with the case included in the study and see if anything can be learned by it. For example, it might be a value that occurs very rarely, but by the occurrence of it in our particular data set, we could learn something about the process under study. So outliers are not necessarily mistakes. They may actually lead to important results that might not have been seen otherwise. I've said before that the regression analysis is not resistant to outliers. Some of those outliers could actually be influential in the sense that if we remove those particular cases, they change the parameter estimates drastically. So it's important to be able to identify those influential cases and know how to deal with them. Now, not all outlying cases are necessarily influential, and there are measurements to test whether or not a case is particularly influential, and those measurements are listed below. Among them are what we call the DF fits, or the difference in the fits, Cook's distance, and the DF betas, which is the difference in the betas. I'll explain each one of these separately, but just for now, I want you to understand that these all leave what we call the leave one out strategy, and that when they're calculated, they leave out an observation at a time, and they're recalculated in times, with each time with one observation left out of the model. The idea being that if an observation is left out and we see a great change in one of these statistics, that would indicate that that observation is influential. So let's look at DF fits first. It measures the difference in fitted values, thus DF fits, for the ith case when all in cases are used versus when the ith case is excluded from the model. So the formula for it, how we write that in formula terms, is that DF fits for the ith value is just the predicted value under the model where all in cases are included, minus the predicted value when the ith case is excluded. And we're going to divide that by a measure of error, which is just the mean squared error from the model where the ith value is deleted, times the leverage statistic h sub I, which we've seen previously. This can be computed also in a different fashion, and here's the formula for that. The basic idea behind this is we can relate DF fits to the studentized residual. So in this case, the studentized deleted residual is given by t sub I, and if we multiply t sub I times the square root of the hat value, or h, the leverage statistic, divided by 1 minus h, we can get DF fits also. So there are different ways to write this, and some are easier to compute by hand than others. But then again, we're using software. We don't have to worry about that. DF betas, or difference in betas, is calculated in much the same way as the DF fits, except now we're looking at the difference in the slopes when we have all in observations in the model versus when the ith case is deleted from the model. So here's the formula for basic DF betas. And again, we have the I slope minus, or the J slope I should say, minus the J slope with the ith observation excluded, divided by an estimate of the variability for that difference. Cook's D measures outlyingness, okay, that's not really a word, but measures outliers, or the distance of the outliers, and leverage at the same time. So it puts them both together, kind of a joint influence statistic, if you will. The plotting of DI, we usually plot it to identify large values. But one of the things we need to remember is that when we remove an influential point, it may have a little effect because there's no another influential point nearby. Removing an influential point could actually worsen the fit because there is an influential point that's opposite it. So when we remove an influential point, we're going to change all of these statistics, and we may actually create more havoc than we actually solve by removing the point. Let's look at an example using some data that analyze body fat composition in humans. Body fat composition, to measure it precisely, is a very difficult thing to do and quite inconvenient for the subject. In this case, it required underwater weighing. But we want to find an easier way to do that, so we want to relate body fat to 3 measurements: tricep skin fold thickness, mid-arm circumference, and thigh circumference. These are fairly easy measures to obtain. Here we can see that actually tricep skin fold thickness, mid-arm circumference, and thigh circumference are quite highly correlated with each other. If we look at a scatter plot matrix, for example, we can look at body fat versus mid-arm circumference and tricep skin fold thickness. The thigh circumference is not included in this case because it is very highly correlated with the triceps variable, so we just went ahead and excluded it from the model. But we can see in this scatter plot matrix that there is a very high correlation between mid-arm circumference and fat, and a very high correlation between fat and triceps as well. So we want to be able to include these variables in the model and look at influential results. So including all of these variables in the model, we have the following output, and we see that for the parameter estimates, again, I've just included the estimates for triceps and mid-arm in this case. We see that we have 95% confidence limits, and the if you look at the variance inflation factors for these, they're huge. 805 and 109. Those are much, much, much larger than 10. So clearly, these two variables are telling us roughly the same amount of information. But actually, that variance inflation may not be due to the variables themselves. It may be due to some influential observations in the model. So we have to check before we remove any variables. So if we look at the linear model results, we have various fit statistics that are plotted here. Let's look at observation 3, for example, in this table. We see that for observation 3, we have the studentized residual as negative 0.133. That's actually not a really large studentized residual. But if we look at the influence statistic, what we call H, it's 0.42. This is a very large statistic, and we probably want to look at this point a little more closely. We keep going. There's another statistic here called the covariance ratio. And the idea behind the covariance ratio is that if the covariance ratio is greater than 1 plus 3 times the number of parameters in the model divided by n, then deleting the observation will adversely affect the accuracy of at least one of the parameter estimates. For this particular model, that threshold is 1.3, and we see that this particular covariance ratio is at 1.5. Again, this is an observation, number 3, that we might want to look at more closely. If we look at the DF fits, we see that that value is negative 1.1. Again, not a very large value, but given the value of the leverage and the covariance ratio, we might want to look at it more closely. And if we look at the DF betas, note that the DF betas have values for intercept, triceps, and mid-arm. So with the DF betas, we can look at the influence for observation 3 on all of the parameter estimates, not just one at a time. It doesn't really have much of an influence on the intercept or on triceps. If we look at mid-arm, again, that does not seem to be, it looks like it's about negative 0.9. That's not a very big observation either. But we still want to keep this one in mind, just in case, because of the high leverage statistic value. If we look at observation 15 down there near the bottom, this one also has a high leverage value and a high covariance ratio. And if we look at its DF fits, those values are not so large. Let's see what happens when we actually remove these. In fact, as I'm looking through these, I don't really see any of them that have very large DF fits or very large DF betas. But some of them have large high hat ratios or height diagonal or leverage statistics, and we want to look at those. So are there influential cases? If we look at the scatter plots that are output from SAS, we can see that for the Cook's distance in particular, there seems to be one observation, which is observation 3, that is rather large. It's at 0.4. It's also the largest value for the leverage statistic. So I'm looking at the plot in the top right, which is the studentized residual versus the leverage statistic, and we can see that there's this dot way out on the horizontal axis. That's observation 3. And if I look at the Cook's D plot, on the vertical axis, that's Cook's D versus the observation. Again, observation 3 tends to indicate that it might be trouble. So what happens if we delete observation 3? If we delete observation 3, here's the result from this, and we see that the variance inflation of both triceps and midarm decreases from values that were way over 100, or at least in the case of triceps, to 1.17. Therefore, any correlation in these two, any redundancy in these two, seem to have been caused by case 3. So actually, sometimes collinearity or the appearance of collinearity in the model can be caused by outlying values or influential values in the model. And note that the parameter estimates are changed a little bit by the exclusion of case 3 as well. And after case 3 is removed, well, we can look at the output statistics, and we note that there are other cases that show up as influential. So case 14, which is actually the old case 15, if you're keeping count, is now at 0.38, so that's still a high leverage point. Its covariance ratio is still large, but its DF fits and DF betas are not that large. We have other values that might be influential as well. We're looking at case 4 with a hat statistic of 0.34, but none of these tend to have large DF fits or large DF betas. So probably the deletion of case 3 was a good idea. It reduced the amount of collinearity in the model. But of course, before actually completing the analysis and assuming that case 3 should be completely removed from the model, I would need to check to make sure that case 3 was a mistake. And if it's not a mistake, we need to include it in the model with the caveat that inclusion of that case makes the model turn out a little bit differently than not inclusion of it. In linear regression, we've talked about testing slopes in the model for statistical significance. One of the key assumptions of the regression model, I'm not talking about necessarily assumptions needed to drive the hypothesis test, but one of the assumptions that we don't normally talk about too much is that the terms in the regression model, meaning the explanatory variables, sufficiently describe the process in question. It's misleading to leave out important variables, and it's also misleading to include nonsensical or non-essential terms in the model. We need to find the smallest model that explains the relationship sufficiently and includes all the explanatory variables that we think are important for the model. So what tools do we have? Well, we can examine data for outliers and influential observations and make decisions about those particular observations if we find any that are influential. We can remove terms that help to answer the study question or to get rid of nuisance variables. I'm sorry, I misspoke. We should remove terms that don't help answer the study question and get rid of variables that we don't think are important for the model. We can look at partial residual plots to see if the removal of a term results in a partial residual plot that indicates that that term should be included in a linear fashion in the model. We can so any term that does not have a linear relationship in the partial residual plot is one that should probably be removed. But be careful. Removing a term that is not statistically significant may change the significance of other terms. Remember, these terms are correlated with one another. It's very likely that explanatory variables in any given model, if we have multiples of them, that they're going to be correlated with each other as well as being correlated with the response. So when we remove explanatory variables from the model, we might be changing the model in a way that we might not like. So we have to be careful and always check the model again and again and again every time a change is made to it. But there may be other methods to consider if we can't get the least squares regression model to work appropriately, if we have too many outliers, or perhaps if we have non-constant variance. One of the ways to deal with that is with weighted least squares. A weighted least squares will weight values with large variance less than values that have smaller variance. In other words, the values that are measured less precisely will get smaller weight in the model, therefore they won't affect the values as much. We can also look at measurement error models. Measurement error models are appropriate when X is measured with error as well as Y. Up to this point, we have been assuming that Y is the only variable that carries any error with it, and that X is measured with no error. We know that in reality that's probably not the case. So measurement error models might be another extension of linear regression models that might be better for your research question. But measurement error is not an issue really when the purpose is prediction, because the prediction error is going to carry through regardless of whether X is measured with error or not. Now, causal relationships between the explanatory and response variable are only possible in randomized experiment. So just because we have a really great regression model that fits amazingly and the R-square is 90% or above, that does not mean that we can say that our combination of explanatory variables causes Y. It may be that we have left out an important variable. It may be that there may be other things that are going on in the model that we cannot take account of. Perhaps the time the data were collected might be a factor, or the group on which they were collected. So even given all of these things and doing the best that we can to get a good regression model, still the only way to look at a causal relationship, or the only way to determine that, only way when we can actually conclude cause and effect, is through a randomized experiment. I've said before that adding a large number of garbage predictors that don't explain additional variance may make the R-square or the F statistic for the overall model become large, and therefore we would have something that we think is a good prediction, but it's not really. So we need to be careful about adding additional predictors to the model. But if we have a large number of predictors, how can we possibly determine which ones are the best? We can look at all the significance test variables, for example. We can see that some of the parameters may not be statistically significant, but if there's a large number of parameters, removing and inserting various explanatory variables is going to change the results of all the other parameter estimates and may result in, well, it's just going to be really confusing. It's going to be very hard to determine which model should be, or which predictor should be included in the model. Now, there are automatic variable selection techniques. I'm going to talk about 3 of those today. They're forward selection, backward selection, and stepwise regression. Now, these automatic principles work on the same idea in that what we're going to do is allow the computer to predict which variables should be included in the model. These work slightly different ways though. So forward selection begins with no predictors in the model. We fit a simple linear regression model for all of the potential predictors one at a time. So the first predictor is included into the model. If it's statistically significant, it's left in the model, and then the next predictor that has the best statistical significance is included. And that goes on until we reach a point where we do not increase the R-squared in the model by very much. So the first predictor that's added to the model is the one, it stays in the model. And we keep adding predictors to the model. backward elimination, let me talk about advantages and disadvantages of forward selection. Forward selection is very easy to compute and understand. We keep adding variables to the model until we come to a place where the increase in R² is so small that it would be statistically significant, and then we stop. It can always be performed even if your sample size is much less than your number of predictors. However, the disadvantages are that it's possible to get a bad initial fit. Maybe the first variable that got entered into the model was statistically significant with no other variables in the model, but we never take it out once it's in there. So bad variables, or variables at least that don't predict the response very well, could be included just because they happen to be statistically significant with the previous predictors in the model. It doesn't guarantee necessarily the best subset of variables inclusion. And we may enter collinear variables at random. There's no check for collinearity in this. Now, backward elimination does the opposite. We start with all of the predictor variables in the model, and for each variable, we're going to compute an F statistic, which tells us how much the overall F decreases when we drop a variable from the model. We keep going until we reach a significant increase in the F statistic, meaning that we keep dropping variables from the model as long as they're not statistically significant, or as long as they don't cause a large change in the R² for the model. And when we get to a point that we have a large change in the R², we stop. For backward elimination, the advantages are that we begin with a good fit. Obviously, having all variables in the model is a good fit. We also have a good initial estimate of the overall error variance. We're only deleting predictors that are not influential. But the disadvantages is that one of the things is that we can't do it if the sample size is less than the number of predictors. We also may have few error degrees of freedom initially, which makes it harder to estimate which values should come in and out of the model, or out of the model, I should say. Again, we're not guaranteed best subset selection in this case, because collinear variables may be deleted by a random process. Again, there's no check for collinearity, and there's no model checks, no residual checks, no check of any kind done at any stage. It's just a procedure to remove variables from the model according to whether or not we have statistical significance or not a large change in statistical significance as a variable is removed. Stepwise selection attempts to marry both of those. At the first stage, we're going to add an explanatory variable. And then at each stage, we perform a backward elimination. So let's say at the first stage, we enter a variable, and then we enter the next variable, and it's determined that the first variable that was entered is no longer statistically significant with the second variable in the model. Well, then we drop the first variable and keep going with the second variable in the model and go back and forth like that until we come to a model where all of the terms are statistically significant. Now, stepwise selection seems to be a really good compromise between forward selection and backward selection. And there are times when these three procedures will actually result in the same model. But there are times when these three procedures don't result in the same model. And then in that case, you really have to just decide on looking at the model, which model makes sense. Perhaps you might even want to decide on the smallest model. That might be a good idea, or it might not be. You want to look at the R², and of course you always want to check your regression diagnostics to make sure variables aren't being included because of influential observations or anything like that. Now, how do we select a selection procedure? No one of these procedures is universally better than the others. So we have to become familiar with what software does. These are obviously all done by software. We don't do these by hand. We can learn as much as we can about the mathematical details and the advantages and disadvantages of a particular method. And if we particularly like the mathematical details of a method, and we know that its advantages outweigh its disadvantages, then that might be the method that we choose. But remember the multiple comparisons problem. We are doing multiple comparisons on data. We are doing multiple statistical significance tests. In the case of stepwise regression, we're not only doing tests for forward inclusion, we're doing tests for backward elimination, back and forth and back and forth. And the more variables you have, the more tests you're doing, which means you're increasing the probability of type 1 error. Most statistical software does not have an adjustment for the number of tests that you're doing, even when you're doing these multiple variable selection procedures. So the number one thing you can remember when you're using these procedures is to use your head. You are smarter than the computer. If you're the researcher, if this is your data, you know these data inside and out, and you can determine which variables make sense to include and which variables do not make sense to include. Perhaps you might want to run one of these automatic variable selection procedures as a first try. Look at what's included, look at the regression diagnostics, check all the influence statistics, make sure all the assumptions are met, and if that's the case, and the explanatory variables that were in the model make sense to you, that they should be included in the model, then that's the model that you go with. If the model doesn't make sense to you, if you can't explain why a particular value has a negative estimate when you think it should have a positive estimate, then maybe you need to go back to the drawing board and do another method of variable selection, or to go through the model again and try to determine in another way which variables should be selected. But ultimately, it's the researcher and not the computer who makes the decision on what variables should be included in the model.
We want to look at variable selection and cross-validation. The dataset that I have here measures percent of body fat in the human body, and actually measuring this is a very difficult task. In order to find density, which is one of the response variable here, in order to find the percent body fat, we actually have to measure, the process is very time consuming. So we want to be able to find measurements that are easy to take and are closely correlated with body fat. So we can get a close approximation to percentage body fat using regression with measurements that are fairly easy to measure. So what we have are data on 252 men. The data are in a file called bodyfatbig on .text on the website. I already have this data set into SAS, and I've already run a bunch of regression code. So what we have are the density determined by underwater weighing. That's a rather difficult process. Also the percent body fat from an equation that's been around since 1956, where the percentage of body fat is related to the body density. The age in years, the weight, the height in inches, neck circumference in centimeters, chest circumference in centimeters, abdomen circumference in centimeters, hip circumference in centimeters, thigh circumference in centimeters, knee circumference in centimeters, ankle circumference in centimeters, biceps with the arm extended circumference in centimeters, forearm circumference in centimeters, and wrist circumference in centimeters. So again, we're trying to get an estimate of body fat using all of these measurements. Now clearly not all of them are necessary, so we have two tasks ahead of us. One is a variable selection task, and the other is a cross-validation task to make sure that the model that we have is a reasonable one. So I've entered the data into SAS, and let's look at, now remember, we don't start variable selection until we have done our best to ameliorate any possible violations of the data, violations of the linear model. So we want to get rid of influential observations. We would like to narrow down any variables that are highly correlated with other ones. We want to make sure that the regression, the residuals from the regression show a nice random scatter in the residual plot, and also have a normal distribution when we look at the QQ plot. So here, from what I've done here is I've run some correlations. I've actually also run a scatter plot, an SG scatter, so a scatter plot matrix of these. So let me go and show you what that looks like. well, that's not what it was supposed to. There we go. There's a scatter plot matrix. Of course, we do have a lot of variables here, so the scatter plot matrix is pretty much at the limit of its usefulness. But you can see a couple things. First of all, you can see that some of the variables are highly correlated, like this is weight here with that's weight with knee, actually. That's rather interesting. We also have these points out here. So we have an individual, for example, whose height is rather small but has a, so this would be height on the vertical here and neck circumference. We also have weight by height here, so this person has a medium weight and kind of a medium height. This person's tall with large weight. But these variables are, we have these couple of dots here that look kind of like outliers, and they might be influential, so we need to look at those very quickly. I also run some correlations, but I'm not going to go through those. This code will be on the websites and along with the data set, so if you want to run it yourself and look at things more carefully, you certainly are very welcome to. Next I have a proc reg where I'm just going to take body fat and throw everything into the model. So that's what I've done with this one, I believe. And notice I got some VIFs for some statistics, so that we'll be able to determine whether or not we have a lot of correlation in the model. Obviously, we have a statistically significant result. The R-square is 0.74, rather almost 0.75. Well, if you look at the adjusted R-square, which we really do need to look at for this model because we have so many independent variables or so many predictors, it's actually just closer to 0.74. And if I look at my variance inflation, I don't see anything that jumps. Well, what I do, sorry, I do see something that jumps out. Weight at 33 and abs at 11 and hip at 14. But that doesn't mean I should delete weight and abs and hip. I don't delete variables until I have figured out all of the, I've gotten a data set that I'm confident meets the assumptions to begin with. So I'm going to go down to this plot, looking at the fit statistics. Here's my parameter estimates. Whoops, that's not where I want it to go. I'll just scroll down. Just have to scroll down quite a bit to get past all these. These are all the fit statistics, by the way, so I have 252 of them. Here's my residual plot. You can see that we do have a couple of observations that look like outliers. I'm going to scroll up a bit more. So I've got a residual plot for every single regressor. Let's look at the leverage. So I see I have one particular observation with a fairly high leverage. It's probably one of those outliers, and here's a second one that's fairly close. So what I'm going to do is see if I can find this individual and delete them. Again, that's not the first resort. I need to investigate that, find out what about that individual makes them a high leverage individual, if they should be included in the model or not, if there's a reason to believe that that individual is from a different population than the one that is of interest. But for the sake of time, we are going to delete that person, and it happens to be observation 39. So how did I find that out? Well, I went back through the data and I looked up the hat matrix value for each one, and this one had a hat matrix value of 0.37. So I've actually created a data set called body 2 where I have deleted individual 39 from the data set. Then when I rerun this data, so that's what this model is, very close to the end. So I'm going to having trouble navigating SAS here. I guess maybe I've got too much in it. It's confused. So get down to this model. Here I have 251 observations, which makes sense. Note that the R-square didn't really change. It actually went up by about 1,000th, which is no big deal, but it didn't change too much. The variance inflation went down, though. Variance inflation is at 30, so removing that observation did help in terms of variance inflation for the variables that tended to be higher than others. So that individual was probably an influential point. But what I'm going to do next, again, I know I have other high leverage values in here. It's very likely that I do. Went too far. Go back up to the leverage statistics. Well, it's actually not too bad. I've got an individual with about 0.2 leverage, which remember that this scale went up to all the way to 0.3 earlier, so that was a much larger scale. If I check out my regression plot, the residual plot actually doesn't show as outliers as distinctly as they were previously. The normal QQ plot looks pretty good. And so I'm actually just going to stick with this for now. The height, evidently we have someone who's fairly small in this data set. So that might be part of the influential statistics. And maybe that person should be removed. So I need to find out who this individual is with a height of about 30 inches. So what do I do for that? Well, I'm going to just print the data. So, well, I probably did that up here at the top. Here's my proc print. Let me find out who this individual is that has a height of 30. I'm guessing that this height was probably entered incorrectly. So if I scroll down, again, this is, I suppose what I could do is something a little more clever. 29.5, individual 42. All right, so that person, now remember also, we also already deleted 39. So what I'm going to do actually is go back to the original body 2 and just change it just a little bit. So 39 had a rather high weight. 42 has a very small height. And then I'm going to just delete those two observations. Again, in the case of 42, I feel very good about deleting that one because it is a rather different height for an adult male. 250 observations. Okay, things look good. 39, again, I probably should check again, although that person did have a very large weight. I believe their weight was 363. So let me rerun this model with everything in it and see if that helped with any of my leverage statistics. It's taking a bit of time. Residuals look good, so I just kind of flip through them. Well, now I have my leverage. I do have a tall value, but it's only at 0.08, so you got to look at the vertical axis. It looks good. The residuals look normally distributed, fairly randomly scattered, and all that. And I'm going to go up here, down a little bit more. Sometimes it's hard to navigate your way around in these things. There's my model. Didn't really change the R-square that much, which is good. Oops, now weight has a really large variance inflation. So what I'm going to do is just delete weight from the model. I'm guessing that these other variables are similar to weight, and so this is the model that I want to use when I do my selection. So now I have a model. I'm actually decided to delete weight, not because it wasn't statistically significant, but because it had a high variance inflation factor. And I believe that there are other variables that will help me that are very similar to weight, will do the same job that weight would do in the model. Leverage looks good, residual looks good. Again, just scanning things very quickly, going all the way up to the top here. This is going to take a while, so let me see if I can do this without passing it. If I scroll up, variance inflations are down to 10 for abs and hips, and obviously weight's not there. All right, now I'm ready to do some variable selection and cross-validation. Now that we have a model that we think is viable and that the VIFs are relatively small and that we think we have taken care of any high leverage values and any violations of the regression assumptions, we would like to be able to choose the features or choose the predictors that are the best fit or the best predictors of body fat. Now, one of the difficulties with automatic variable selection methods, which of course we pretty much have to use since we have so many variables, is that they don't work on data other than those that were used to calculate the model. By don't work, I mean that they don't give good results, or maybe the R-squares are a lot smaller than you would normally expect to see if you had for a new data set, even if the data set has the same variables as previously, just collected on different individuals. So one way to ensure, or assure, I guess, that a model found using an automatic selection method is valid is to use it on another set of data. But we don't often have another data set. So I don't have another data set of 250 observations from a body fat with all of these variables in it. I wouldn't have to have 250 observations. I would just have to have something, a different data set with all these observations taken on different individuals. But I don't have that. So the next best thing I can do is to divide the data into two data sets. One can be used for training and the other can be used for test. The training data is used to build the model and the test data is used to validate the model. This data set is fairly large. It's 250 observations, but it's better to test the model on as many data sets as possible. So since I don't have multiple data sets on body fat percentage, I can leave out some of the observations in the data that we have. So we train the model with a certain percentage of the observations and then test the model on the remaining percentage that's left out. We do this over and over again so we can understand the impact of leaving out different parts of the data set, and this method is called cross-validation. It's useful for any kind of large data set where you have to make feature selections or you're not sure whether your data, your results, would be applicable to a different data set. So let's look at this code to perform a cross-validation feature selection with this particular data set. Here we have proc glim select now instead of proc reg. Proc reg will do forward, backward, and stepwise selection, but it will not do cross-validation. So in order to do cross-validation, we need to move to glim select, or GLM select if you prefer. We have our data that are fairly clean at this point. They've been corrected as far as we know how to do, and our model with all of the variables in the model. Then we have a selection criterion, which is forward, and here's where I get the cross-validation selection. I say stop equals CV, which means that I want the forward selection to stop when the cross-validation criterion has reached an optimal level. And that criterion is something called PRESS, or it's a statistic that calculates the residual sum of squares for each step, and we want that to be as small as possible. Then we have our CV method is random 5. What does that mean? It means that the data set is going to be divided into 5 parts. So we will have 250 divided by 5 observations in each one of the data sets, and we will run the model on one of the parts and then test it on the other 5 and do this multiple times until we come to a good model with a strong or a small, is what we want, CV press statistic. Then we have also, I asked SAS to print out adjusted R-squared, so we can look at the adjusted R-squares too. Now I actually already have the results up. I've already run this and I have them up. So here we have the glim select procedure. Here's our body, our data set, the dependent variable, forward selection method. There's a select criterion called SBC, that's Schwarz's Bayesian criterion. I'm not going to go into exactly what that is now. We will talk more about selection criterion in the next course, but for now you just need to know that that value needs to be small, or small as possible, in order to, that's one way we can select the model using that. We select the model that has the smallest SBC. The stop criterion is cross-validation. We already talked about that. It's a random cross-validation. There are other ways to split up the data set, but I chose random with 5 folds. and we can keep going. It gives me a random number seed, and that's so that if I want, I can recreate this analysis by putting in this particular seed into the random number generator. 13 effects, number of parameters, all that's kind of a sanity check to make sure SAS did what you thought you asked it to do. So here is my model. The first one into the model is intercept, obviously. Here's my adjusted R-square, as those are included. ABS is included, and you can see how the R-square jumps up. So that's the first one to go in. And you can see how the SBC and the CV press change. Both of these go down. So remember, CV press is a residual sum of squares, so we want the residual sum of squares as low as possible. The SBC criterion we also want to be small as possible. And so at this point, once we have abs, wrist, height, and age in the model, then we stop. SAS says that it has reached the optimal value or a local minimum for the cross-validation residual sum of squares. And the next one that's entered, chest, gives a higher sum of squares than the previous one, so that's another reason to stop. So here we have just model statistics that you usually get from a regression output. We have our analysis of variance with our F value. Our F value is 172.83 on 4 and 245 degrees of freedom. I would say that's statistically significant, even though the p-value is not given. We have our root mean squared error, our dependent value, mean, that means the mean of the response variable. So remember, the response variable is body fat, so regardless of anything else, just taking the mean of the response variable of body fat is 19, so on average there's 19% body fat for these men. Our R-square, our adjusted R-square, various criteria, and we keep going down to the bottom. And here we have our regression equation. So our intercept, we have 2.9 plus 0.056 times age minus 0.322 times height, or 323 rather, times height, plus 0.771 times abs minus 1.911 times wrist. Now, I don't know about you, but I'm thinking that height and wrist being negative is a little weird, so I'm a little suspicious of what the forward selection criterion has given us as a good model for this particular regression. Being suspicious, of course, I would want to do different selection criterion, so I want you to go back to this SAS code. It's already there for you. If you run the code, the previous code I have in the notes for this video, it has all of the selections that we made, so you can get the same data set that I had. For forward selection, we've already run it, so you know what the model is. I want you to run it for backward and stepwise. Examine the model, examine the criteria, look to see what you think is the best model. So if you look at R-squared, the CV press, and you look at the model itself, we want a model that not only has good statistics in terms of a large R-squared and a small CV press, but also we want a model that makes sense. Another thing we have not done, and that these automatic variable selection procedures do not do, is test for diagnostics. So another way to decide whether or not your model is good is to look at the diagnostics for that particular model. So looking at diagnostics and the sense of the equation and the statistics that are out of you get from GLIM-select, determine whether or not forward, backward, or stepwise, determine which one is the best method and state your reasons for doing so. I'd like a 3 to 5 page write-up. If you can do it in less than 3, that's great. Stating your results and the equation itself and why you chose the method that you chose as giving you the best equation. Now remember, just because we choose one of these methods, forward, backward, or stepwise, as giving us the best equation does not mean that it is the best equation. We could find another method or something else that makes more sense to us. But this is what we have for now, and so we're going to try to use these 3 methods to determine which variables are the best predictors for body fat.